I have established by this time the law of conservation of momentum. And as is typical for a lecture series in physics, it's time to look at that law in sort of a practical way, to take it out for a spin, solving problems, and see what sort of observations I can make about the behavior. So what I have, starting again, is my Newton's second law, which I'll just reiterate. The sum of all the forces is equal to the rate of change of the momentum. I've left the harpoons off because I understand that both the force and the momentum are vector quantities. And so when I rearrange this, I get my impulse law that the change in momentum, the total change in momentum, is the integral of the net force, and these forces being external forces, because I know forces internal to the system are action-reaction pairs, and they sum to zero. So the sum of all the external forces dt. And if I can arrange my system in such a way that there are no external forces, in the absence of external forces, then my expectation is that the change in the total momentum of the system, when I say total momentum, I realize that what I mean is the sum of the momenta of all of the particles in the system, or objects, or whatever it is in the problem I'm trying to solve. The change in momentum is equal to zero in the case that there are no external forces. That's the criterion. So let me apply this to a simple physical situation and see what I can learn from it. This is the simplest problem that I can possibly solve. There is nothing essential about this, but it's just a very simple application. So in the absence of any external forces, imagine that I have a block here that I call A, and it's moving along with an initial velocity that I call VA. Notice that I'm not using VA not. There's nothing I could do. I couldn't avoid that. Because the final, I use primes, remember, so you'll see me using primes in this notation. So here's VA moving along, and it's moving with a velocity, and here's B moving along with a velocity, VB. And I'm actually going to give these some values for purpose of calculation to see what happens during this collision. So obviously what I want to do is select for A a velocity that's sufficiently large that it'll catch B. Otherwise they won't collide at all. So what I'm going to do is say, let's let the mass of A be equal to 1 kilogram. And let's let the velocity of A be equal to 2 meters per second. For B, I'm going to make B more massive because I get a more general result if I don't assume that the masses are equal one to the other. So the mass of B, I'm going to make equal to 2 kilograms. And for a little amusing symmetry, I'll make the velocity of B equal to 1 meter per second. So you see what I've done is that these two objects are moving along in such a way that A will eventually catch up to B and they will collide. When they do, there will be forces of interaction whose nature I do not deeply understand, and I do not care to, because, according to Newton's third law, there'll be action-reaction pairs. They add to zero, and I don't need to concern myself. What I do concern myself with is, notice I have not put these two blocks on a surface with friction. If I did, then the friction would be an external force, and I would not expect that momentum would be conserved during the interaction. So the one catches the other, they collide, and I'm saying that it's a particular feature of this collision. It certainly does not happen all the time. But it's a feature of this collision that when the two collide, they collide and stick together. So here's A and B now stuck together. They do not stick together and stop. I'm going to prove that just by solving the problem. But here they are stuck together, and they're moving along with some final velocity that is a mutual final velocity V prime. That is, the velocity of A after they collide is equal to the velocity of B after they collide is equal to, I'll just give it a name, V prime. And so what I would like to do is to apply the law of conservation of momentum to this situation and see what I can figure out. Well, what I figure out is rather obvious because I'm going to write that the total initial momentum of the system, which I'll simply call P, is equal to the total final momentum of the system, which I'll call P prime. So it's up to me now to calculate how much momentum that I have. Well, that's a very simple thing to do because the momentum before and after the collision is found simply by adding the momenta, that is MAVA plus MBVB. Now, algebraically, I've written that as plus. Algebraically, I've written it as plus. But you have to be careful. The momentum is a vector quantity. Now, of course, the mass is a scalar quantity, so the vectorness of momentum comes from the velocity. Either one of these velocities could be negative, and that could introduce a negative sign into my algebra. I have to be cautious that I'm dealing with a vector equation, not a scalar one. And I give that caution, I think you realize, because you just finished doing a bunch of energy problems where the kinetic energy is always a positive quantity, and if you choose the lowest configuration of the system to be zero, then potential energy is always positive, and so you didn't have to worry about algebraic signs. You want to be careful here. This is a vector equation. that I'm writing. So the total initial momentum is equal to the final momentum, which is the mass of... I threw away the wrong marker. Did you see that? Here I go, picking through the trash like some sort of physics hobo. There we go. So the momentum after the collision, which is going to be MAVA prime plus MBVB prime. That right there is a general expression for the law of conservation of momentum between two objects which collide the one with the other. And so now all I have to do is flesh it out and see where it leads me. Well, I can plug in some numbers quite easily. Here I know both the velocities VA and VB are positive, 2 meters per second and 1 meters per second. So the mass of A is 1 kilogram times 1 meter times 2 meters per second, is 2 Newton seconds of momentum. Plus the mass of B is 2 times 1 meter per second is 2 Newton seconds of momentum. So on the left-hand side, I have 4 Newton seconds of total momentum. That is the conserved quantity. That is the number that I have calculated that will not change because momentum is a symmetry. And I expect the sameness of that number. On this side, I have MAV, but these velocities are the same. So I have the mass of A, which is 1, times V prime, because VA is just the final velocity, final mutual velocity of both, plus 2, because the mass of B is 2, VB prime, but VB prime is V prime. So on this side of the equation, I have 3 V prime. And so what I find is that the final velocity of the two after collision is 4/3. I'm going to actually throw some units in here now at the end. 4/3 of a meter per second, according to the units that I've chosen to solve the problem, V prime. So that's a very simple thing to do, and it's not a remarkable result. But what is remarkable about it is that I was able to find a velocity at some time later without considering the forces at all. From a Newton's law standpoint, I understand the way the forces work. That allows me to calculate the acceleration. And once I know the acceleration kinematically, I can predict the velocity in the future. But here, I've predicted a future velocity without using any forces at all. So it's rather remarkable and extraordinarily useful thing to do. Extraordinarily useful thing to do. I'm a little bit curious, though, about what would happen if I applied the work-energy theorem to this situation. That is, what if I went about calculating the kinetic energy of the system? It's easy to do because now I know all of the numbers. Well, if I calculate the initial kinetic energy of the system, I would do that by calculating the sum of the kinetic energies. That is, the initial kinetic energy of the system, which I guess I call K0, the initial kinetic energy, because that's how we do our notation. I guess I could call it K. I'll call it K and K prime, just to play along with the momentum. So K is equal to 1/2 the mass of A times the velocity of A squared plus 1/2 the mass of B times the velocity of B squared. And it would not matter at all if either of those velocities were negative, because the square and the kinetic energy would turn that number positive. But in fact, they are both positive numbers. So what I have here is 1/2 the mass of A times VA squared, but VA is 1, so 1 squared is 1, is 1/2. Plus 1/2 of a joule is what that would be. So here, 1/2 MB, well, MB is 2, or I did it wrong, didn't I? I made a mistake. Pardon me, let me start again. Calculating the kinetic energy of A, the mass of A is 1, the velocity of A is 2, so 2 squared is 4, 4 divided by 2 is 2, so I have 2 joules of kinetic energy. For the kinetic energy of B, I have 1/2 the mass of B, the mass of B is 2, so that cancels the 2 in the denominator, the velocity of B is 1, 1 squared is 1. So I start out with 3 joules of kinetic energy, and then the collision takes place, boom, and then after collision, how many joules of kinetic energy do I expect? And hands immediately go up, and everybody says, obviously, 3 joules of kinetic energy is what I'll get. Final kinetic energy, K prime. The final kinetic energy is going to be 1/2. Now the objects are stuck together as one mass. So it's MA plus MB times the final velocity, V prime. Well, what's this when I calculate with numbers? MA plus MB is 3, so it's 3/2. Oh, pardon me, V prime squared. 3/2 times what squared? Well, V is 4/3, and I have to square that, and that works out to 8/3. Yeah, 16/9 is 8/3 of a joule. Energy's lost! Energy's lost. Momentum is conserved. Energy is not. Energy is served. Why, momentum is conserved, pardon me. Energy is not. Energy is not. If the kinetic energy changes here, what did the work? Because work energy theorem tells me that the change in kinetic energy work. What did the work? What forced the work that changed the kinetic energy? It's actually the collision force. The collision force is the only force that acts. The collision force does work which changes the kinetic energy, which means the collision force does non-conservative work. The collision force does non-conservative work. The thing that blows my mind, and I actually thought of this morning, it's a wonderful thing. It's a little bit of an aside. It's a wonderful thing that I can have teaching physics for as long as I have, like more than 20 years. I never even figure out how many years it is. And I can still find new things to think about, right? I know, I'm going to say something silly. I'm going to say something rather emotional about physics. Pardon me. The momentum is conserved and the kinetic energy is lost. How does it know? Like the universe is taking care of itself. Work is being done during the collision. I do not care how complicated the forces are. If this were two things that crumpled and smashed and whatnot when they hit each other, and there were a profusion of forces, it would work out exactly the same. Exactly the same amount of kinetic energy. It feels to me like the power of universal law, that like the universe is following rules that are so strict that they work even when there's sort of unseen action happening, taking place. Energy is lost. So when momentum is conserved, and in collisions, because in collisions the third law applies absolutely, momentum is conserved absolutely. If the external forces are zero, the momentum is conserved. Energy? Not necessarily. There are no potential energies here or anything. The kinetic energy changed because non-conservative work was done, which unconserved the kinetic energy. Energy is lost during collisions. Now, here's the thing I've been thinking deeply about for a number of years. Is it true that in all collisions, energy is not conserved? I mean, certainly I've given you one example where the energy is not conserved in a collision. That's certainly true. But is the energy conserved in is there any collisions where energy is conserved? The answer, so far as I can tell, is no. Because in every collision that I can think of, there is some mechanism by which energy is transported away. Some example. They're really, really simple, obvious ideas. If two things collide, they often make a sound, don't they? That sound is sound waves traveling away. In order to vibrate your tympanic membrane, there has to be some energy. That energy was delivered from the collision to your ear. Energy of the collision cannot be conserved because energy has to escape the collision in order to be detectable in the form of sound, right? Some things, when they crash together, they bend and they deform out of shape. Like two cars collide and the fender gets bent. It takes work to bend the fender. That work is non-conservative and the bent fender absorbs the work. What happens to that work that's done on the bent fender? It's converted into heat because when two objects collide the one with the other, it causes their molecules to vibrate, which is that average vibration of internal molecules we interpret as temperature. And that thermal energy is eventually transferred to the surrounding atmosphere and blows away. Energy is not conserved. You say, no, Charlie, I got it. You see, you take an electron and an electron and you shoot them at each other, right? And the two electrons approach, and we know they repel each other. I think we generally have that idea that two electrons will repel each other. So they come close to each other, but they never touch, and they bounce off each other. There's a collision in which energy is conserved, right? Because they don't make a sound, right? Their kinetic energies change because they interact one with the other, but it's not temperature. So there's no thermal energy, and there's the concept of thermal energy doesn't even exist. And so they come together, they go like, I got it. No, sorry, energy is not conserved for a reason that you're not aware of. When a charged particle, like an electron, accelerates, it emits electromagnetic radiation. So if I have two electrons and they go like that, it emits light waves that carry energy. So it's not even conserved when fundamental particles collide. You say, oh no, Shadley, I've got it. Imagine that I have a planet here, and I have an asteroid comes in, and it interacts with the planet. It doesn't touch the planet, it just comes in and interacts with the planet. It's like a collision, and it goes away, right? Gravity, vacuum of space, right? Energy's conserved? No, because just a month or two ago, they discovered the gravitational waves. When the asteroid comes in and interacts with the thing, it emits gravitations that carry energy. So far as I can tell, and I've thought really hard about it, there are no interactions where energy, there are none. But there are interactions where it's approximately, where it's like very nearly conserved, where for all intents and purposes, it's conserved. So like within the uncertainty of my experiment, there are situations like that. I'll give you an example in just a moment, but I wanted to show you these, which are a great deal of fun. Here are these two rubber balls, and they're identical. See, they're identical in mass. They feel the same. They taste the same. Yep. Smell the same in every way. What's that? Well, that's true, but let's say that the mass of the saliva that I just added to, right? Identical rubber balls. And when we're kids, we get these, you get it out of a gumball machine like the Super Ball, and you go like in your small bedroom and you wing it at the wall and it bounces around all over the place, and your brother's like, stop, right? Rubber ball, identical. Yeah? Yeah. Shall I do that again? The one ball absolutely does not bounce. The other ball bounces quite vigorously, right? This kind of ball we typically refer to as a super ball, right? And it's a super ball because it's just so bouncy. That's what a child would say. But what you would say is that it's so very elastic. Because when a rubber ball like this bounces, and it collides with a surface, it compresses, but it compresses spring-like. It compresses kx-like. It compresses 1/2 kx squared like, and that's conservative. And that's conservative. And so when it crushes, if we watch it in a slow-mo camera and the ball crushes, we see it compress, but that's like compressing a spring, and that spring can give the energy right back. So as it falls, it gains kinetic energy, it compresses like a spring, and it gives the kinetic energy all back again. That's not true. You can tell, because it goes from this height, and it does not bounce to the same height from whence it was released. In fact, this particular ball doesn't bounce as well as some of the super balls I've had as a child. They bounce very, very well. This one's not as enthusiastic, but this is called, in physics ease, this is called a happy ball, and this one is called sad. It probably does bounce a bit. Yeah, you can hear it. Actually, you can hear it tap twice. So it bounces a wee bit. This ball is not elastic. It is not spring-like. Now, we're not going to do it, but if we cut it open, we would find that it's internal structure. And so what happens is when this ball hits, work is done on the inside of the ball to rearrange the internal structure of the ball. A way that you can do this is you could make a rubber ball like this, or you have a rubber ball like this, and then you take a balloon and put some sand in it, and you drop, the rubber ball bounces, a balloon full of sand just hits and does not bounce at all. And the reason why is that work is done to reconfigure all the little sand molecules inside, and all of that little frictional work generates heat, which is all initial gravitation. Elastic, inelastic. Now the fact of the matter is, there is no such thing in collisions as perfect elasticity. Even if this thing was a spring, if I take a spring and boing, 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 doesn't the metal of the spring heat by the stretching and compressing, right? So energy conservation is an approximation often. Energy conservation is an approximation, but we talked about that, how energy escapes the. And so most of the time we apply the law of conservation of energy, even though it's a brilliant law, which is absolutely true, the fact that we enclose it in a system means that energy is not necessarily conserved. It's only approximately conserved.